Hi, my name is Nick Borson, and this is the 7th in a series of videos about learning to program using PowerShell. These videos are all aimed at non-programmers who want to learn to code, and they use PowerShell as a first programming language. The videos kind of build on each other, so if you haven't already, you might want to go back and start at the beginning. I'll include a link to the playlist in the description. So in this video, I'm going to talk a bit about numbers, numeric types, and how numbers are represented in computers. In the last video, I used the shift left and shift right operators, and I kind of glossed over it a bit, but I did mention how computers naturally use binary or base 2 digits to represent numbers as opposed to decimal digits that we tend to use in everyday life. So we're going to go a little bit more into that in this, and we'll talk about the different types of integer types, and also go a little bit into floating point numbers and the different floating point types and their limitations. So let's go ahead and get started. Okay, so a binary number is base 2 as opposed to a decimal number, which is base 10. Let's kind of review a little bit what we mean by base 10, just to kind of set us up for understanding binary numbers. So when we work with ordinary decimal numbers, and we just want to count, say, we have 10 digits to work with. We have 0 through 9. So if we want to count, we start at 0, and then 1, and 2, and so on. We get up to 9. And then if we want to write a number bigger than 9, we don't use a different symbol. We only have these 10 digits to play with, 0 through 9. So instead, we put a 0 in the 9's place. We roll over to 0, and then we write a 1 in the tens place. So we use this positional notation where this column represents ones and the second column represents tens, and so on. And then we count to 11. We again increment the ones place. And this number here is understood to mean 1 times 10 plus 0. And this number is 1 times 10 plus 1, and so on, which is 11. 12 is 1 times 10 plus 2. And this continues on. We get to 99, say. And then we want a bigger number bigger than 99. This rolls over to 0, this rolls over to 0, and we put a 1 in the hundreds place. So this is the 100s place. So here we have the number that's 1 times 100 plus 0 times 10 plus 0. And of course, so if we want to write down a bigger number, 5,287, say. So this is the ones place. This is the tens place. The 2 is in the hundreds place, which is 100 is 10 times 10, so it's 10 squared. A 5 is in the thousands place, which is 10 times 10 times 10, so it's 10 to the third. And the tens place, where the 8 is simply 10 to the first. And the ones place, where the 7 is, 1 is simply 10 to the 0. So the position of the column is just the exponent. So binary numbers really work exactly the same, except that instead of 10, we have 2. So we only have 2 different digits to work with, 0 and 1. And then each column or each place is a power of 2, represents a power of 2. So if we have the number, we start with the number 0, and then we can write the number 1. But then to go bigger than that, we don't have any more symbols beyond 0 and 1, so we go to 1, 0. But instead of this being 1 times 10, it's 1 times 2, because this column, the first column is the ones column again, which is 2 to the 0, right? The next column is the twos column, which is 2 to the 1. So the value of this number here, of the value of the number 1, 0, is 1 times 2 plus 0. And the next number after that, if we keep counting, is we're going to increment the number in the ones place again. And then adding it again, these numbers roll over to 0, and then we put a 1 in the next place, which is 2 to the second, or 4. So this number is 1 times, well, just to be consistent, I'll stick with red here. This number is 1 times 4 plus 0 times 2 plus 0, and so on. If we keep going, we can get to here after a while. If we just go up to 4 digits, the biggest 4-digit number would be 1111. Just like the biggest 4-digit decimal number would be 9999, the biggest 4-digit binary number, or base 2 number, would be 1111. And this is the 2 to the 3rd place, which is 8. So this is 4. So this would be 8 plus 4 plus 2 plus 1, which is 15. In decimal is 15. And it's convenient sometimes to be able to refer to be able to have a shorthand notation for binary numbers. So another notation that's often used in computing is base 16. And the reason we do that is because a single digit can go from 0 to 15 in base 16. So each pattern of 4 binary digits corresponds exactly to 1 hexadecimal digit. And the hexadecimal digits are numbered 0 through 9 and then A through F. So F is 15. So the hexadecimal, the binary digits 1111 equals F. 1110 equals E, and so on. We have 1 is simply 1, 2 is, or 10 is 2, etc. 11 is 3, and eventually we get up to 9, and then A, B, C, D, E, and F. So we'll talk a little bit more about hexadecimal notation later, but that's the basic idea of binary numbers. Now, the various types of integers that we have in computing are generally often have a fixed number of bits to them. So if you're working on paper, say, and you want to write down a number, and you have only a fixed amount of space, a fixed room for a fixed number of digits, then the biggest number you can write is going to be limited by the number of digits. So let's say you only have 6 digits to work with. The biggest number you could write would be 999,999, right? Because you have 6 nines. In binary, the number of digits you have to work with is based on how many bits, because the computer actually has memory that it uses to hold a number. So how much memory, how many bits of memory are used to hold the number is going to determine the largest possible value you can hold, or the number of different unique values you can hold. So let's say that you have, so for example, when we may have noticed before sometimes when we saw the type of a number, it said it was an int 32. Int 32. So the 32 here, in case you wondered, means that this is a number that is an integer type, integral type, so it holds whole numbers, positive and negative, and it has 32 bits allocated to it. So it actually is represented using 32 binary digits. So I'm going to start talking, this is a signed type, but because it has 32 32 binary digits, the number of possible values, distinct values it can hold, is 2 to the 32, which is a little more than 4 billion. Now, some of those numbers are for negative, and some of those are for positive. So it actually can't, the biggest number it can hold is less than that. It's actually 2 to the 31, which is about 2 billion, a little bit more than 2 billion. We also have unsigned types like uint32. So a uint32 can't hold any value smaller than 0, but it can hold values all the way up to 2 to the 32 minus 1. That's the largest value it can hold. But the smaller type would be something like, let's say, an 8-bit type. That can only hold values less than 2. It can only hold 2 to the 8 unique values, which is 256. So it used to be that characters were 8 bits because well, anyway, I won't go into characters. But so any number from 0 to 255 could be fit in a single 8-bit type, which is called a byte. So if you hear things referred to as bytes, then those are 8-bit types. There also are 16-bit types. So 16, 8, 16, 32, and 64-bit types. A 64-bit integer can hold quite a large value. So let's actually get into code a little bit and take a look at what some binary numbers look like and some things we can do with them. Okay, here I am at a PowerShell prompt in my terminal window. I'm going to cd into my learn ps directory where I've been saving all of my scripts. And the first thing I want to do is let's just display some numbers. So I'm going to say for each %n in a range, I'll say 0 to 16. And I'll just say %n. So this is just going to display the number in decimal form. Now, what if we want to show the number in hexadecimal form? There is a way we can do that. So I'm going to have a string, and I'm going to actually represent, I'm going to first put the number in decimal form in the string, and then I want to say in hexadecimal form. The way I can do that is I can use this. I can say left curly brace, like so. Okay, so I'm using this is a bit, takes a little bit of explaining here. This is the -f is the format operator. And this is taking the string and formatting the string and using this as on the right-hand side as an argument. So this is an argument that's going to be substituted for a value for an expression in the string. So I could also, if I want to, here I can just say 0. I think that'll work. I think I made a mistake there. Maybe I have commas here. Yeah. Okay. So now that we've seen the output, let's take a look at this. So this excuse me, this 0 in curly braces means that when I format the string, this is going to refer to an argument that's separate from the string itself, an argument that's going to be at position 0. So we have a sequence of arguments here. In this case, they're both the same. Actually, I don't even need the second one, do I? They're both at position 0. Okay. But I can have a sequence of arguments, 0 or more arguments, or probably 1 or more arguments. When I'm doing this, I'm going to have an argument. And then I can refer to these arguments by their 0-base index. So here I'm saying I'm going to take the value at the argument at index 0, which is the value of n, and insert it at this position in the string. This one is exactly the same, except I have this :x after that. And the :x means that I'm going to format this number as a hexadecimal number instead of a decimal number. So when we see the output, on the left-hand side we have decimal numbers counting up from 0 to 16. On the right-hand side we have the same numbers represented as hexadecimal. So we go from 0 to 9, and then we count up using A, B, C, D, E, and F. And once we get past 15, we don't have any more hexadecimal digits to play with, so we go to 1, 0. 1, 0 in hexadecimal being 1 times 16 plus 0. So there's hexadecimal. Now what if we want to look at some binary numbers? We don't have a ready-made way that I know of to display binary numbers, but let's just write a little script. I'm going to create a new script. So as usual, I'll just invoke Visual Studio Code by typing code, and I can type any file name I want, and it will open that file, or in this case, I'm going to create a new file by typing a file that doesn't exist. So I'll call it numbers.ps1. I have to give it the ps1 extension so that PowerShell will treat it as a script. Okay, so I want to take a number, and I want to convert it to a string of hexadecimal digits. So let me write a little function then that takes the number and returns an array of binary digits. So I'll say function get binary digits, and it takes a number as a parameter. I'm just giving the parameter the name number. I could call it n or whatever. Okay. So I'm going to write a loop. I'm going to be, let's say I'm just interested in 16 digits. I'm just going to limit myself to 16 bits, 16-bit numbers. So I'm going to write a loop then that's going to go from, I'm going to start with the highest. I want the digits the lowest order digit, the least significant digit is the digit at position 0. But the first digit we write is going to be the digit at the most significant digit, which would be at position 15. So I want to have a loop that counts down from 15 to 0. So I'm going to write a for loop for that purpose. I'll say for, and I'll say, well, call my loop variable bit index, because we're going to be using this variable to be the index of the bit, or the position of the bit, starting at the least significant bit being bit 0, and then counting up from there, the next bit over being bit 1, and so on. So bit index, I'm going to start with bit 15 for the first iteration of the loop. I'm going to keep going as long as bit index is greater than or equal to 0. And then after each iteration, I'm going to decrement bit index. So we've used the increment operator plus plus that adds 1 to the number. Here I'm going to use the decrement, oops, somehow I changed my focus. I'm going to use the decrement operator minus minus to subtract 1 from the bit index. So maybe before I do anything else, let's just actually see what happens. Let's just write the value of bit index to the output so we can see what that looks like. So I'm going to, so far we just defined a function. Let's call it get binary digits. And let's run our script and see what this does. So I'm going to clear the screen. Numbers. Okay, so as we expect, it just counts down from 15 to 0. So we're going to loop 16 times, because 0 up to and including 15 is going to give us 16 iterations. And each iteration, we're going to start at 15, count down to 0. And we're going to, now we want to get the bit, the corresponding bit in the number. So there are going to be a couple of techniques we're going to use here. So one thing that when you have a number like, let's say we have a binary number like 10 10 10 0 0 1 0, whatever. Okay. I'm just going to separate out. Let's say 1011. I'll just keep it simple, nice and short. Let's say we want to just refer to, we just want to find out if this bit, we just want to get the value of this bit. Right? So if we just ask if the whole number is 0, it's going to ask us if you know, it's going to look at all these other bits. But what we'd like to do is mask off the other bits so that we can just keep this bit and make the others all go to 0. So how do we do that? Well, one way we can do it is we can do a AND operation, use a bitwise AND operation, and we can create a mask. So this is our mask. This is the value that we're and when we do a bitwise AND, what we're actually doing is we're computing the logical AND of each bit with the corresponding bit on of the two values. So here we're going to take the logical AND. So AND being an AND in this case being, so first of all, we always treat 0 as being false and 1 as being true. And something is an AND operation, A and B, say, is only true if both A and B are 1. Well, A and B is 1 only if A and B are both 1. In fact, we can describe AND using a little truth table, right? So we have A and we have B, and we have A and B. Okay, so there's only 4 possibilities here. If we have a function with 2 binary values, we can have both be 0. We can have one or the other be 0, or excuse me, one or the other as being 1, or they can both be 1. So there's only 4 combinations of these 2 bits, right? So we can say, what should A, if considering 0 to be false and 1 to be true, if both A and B are false, well, A and B is, of course, also false. If only one of them is true, then they're not both true, so A and B is also going to be false. The only case where A and B is true is if both of these are true. Okay, so now let's look at these 2 numbers and look at each column as a separate AND operation. So this, looking at this column, the first column, the leftmost column, 1 and 0 is going to be 0. And 0 and 0 is going to be 0. 1 and 1 is going to be 1. And 1 and 0 is going to be 0. Now, when we look at the mask, we see that all the bits but the one we're interested in are 0. So what that means is all the columns of the result, so this is value, so hyphen B and is the bitwise AND operator in PowerShell. So all the columns so if we have only 1 bit true in the mask, all the columns in the result are going to be false except for that column. And that column is going to be 1 only if the column of the value that we're testing is 1. So let's say we want to test the next position over. Let's look at, again, we have 1, 0, 1, 1 is the value. And we have 1, or 0, 1, 0, 0 is the mask. Oops, that's weird. Why did that happen? Sometimes the editor is trying to cleverly suggest something to me. Okay, again, let's look at the leftmost column is going to be 0 because the mask bit is 0. This next column, the mask bit is 1, but the value, the corresponding bit in the value is 0. So they're not both 1, so again, it's 0. And then the remaining 2 bits are both 0 in the mask, and so they're not going to be 0 in the result because both have to be 1. So in this case, value bitwise and mask is going to be 0. So you can see how how using this bitwise and can be used when we in conjunction with the mask to test whether a specific bit we're interested in is non-zero, is 1. Okay, so I'm going to erase all that. You can always pause the video if you want to keep it. And what we're interested in now is testing whether the particular bit at the index, we're starting from index 15 and counting downward, the bit at the current index is 1. So what we can do is we can create a mask that has only that bit set, and we can do so by saying mask equals 1 shift left by the bit index. So again, so here we're using the shift left operator, and all that's doing is it's moving all the bits to the left by this number of places we specify. So for example, if we have a binary number like this, then we shift it left by, well, let's just say shift left by 1 place, then we get 0, 0, 0, 0, 1, 1, 0, 1, 0, right? We shift it left, we moved it left by 1 place. Shifting it left by 2 places is going to give us, right? Each time you shift it left a little bit more, we move it over a little bit more. So we start out with 1 because 1 just has the lowest order bit set and none of the other bits set. By shifting it left a given amount, we're shifting our 1 bit over so that we can mask off the bit at the position we're interested in. Okay, so we're going to create a mask such that where only the bit we're interested in is 1. Okay. Then we can say number if number bitwise and mask is not equal to 0, then we can write a 1 for that digit. Otherwise, we can write a 0 for that digit. And if we're not confident about the precedence of these operators, we can just make it clear that we're evaluating this expression first, use parentheses, we're evaluating this expression first, we're masking off so that only the bit that we're interested in of the number is all the other bits except the bit we're interested in are going to be 0. And the other bit, the bit we care about, is either 0 or 1, depending on its actual original value in number. And then if the result is not equal to 0, then we know that bit was 1. Otherwise, that bit was 0. So let's try this. And let's try a few different numbers here. We'll say for each %n or $n in, and I'll go from 0 to 15. Get binary digits $n. But this function is returning an array. I actually want it, I'd like it to be represented more concisely, so I'm going to join all these digits up so that they're in a single string. All right, let's try that. What did I do wrong here? Oh, I only have a... Okay, so now we're executing from 0 to 15, and we see this is what it looks like to count in binary. So we start with all bit 0, then we have the ones place is set to 1, so that's our number 1. Then we have the twos place is set to 1, so that's the number 2. Then the twos place and the 1 place is set to 1, so that's 2 plus 1 is 3. Then we have the fours place is set to 1, so that's 4. Then we have the fours and the ones place, so that's 5. And that's the fours and the twos place, so that's 6, and so on. So here, just for fun, here let's we can function get binary and this we'll call join Okay, so we have a binary representation. Let's go ahead and write out a output where we have a decimal, binary, and hexadecimal representation. Or we'll do decimal first. So let's see. We're going to use this this format thing again. So first we'll write the decimal. So here we'll say. So the number is $n. So this is simply saying the first argument, the argument position 0, so that's $n. We're going to write that out as its default format, which is decimal. Then we'll write the same thing out. We'll write it out in hexadecimal. And then we're going to write out the second argument, the argument at position 1, which is our binary number, which is a string that we created using this code up here. Okay, so in decimal we have, let's go all the way down here, decimal we have 15 is the hexadecimal F, and it's binary 1111. And we can see that that each hexadecimal, we go up to 4 digits, and each hexadecimal digit corresponds to, well, we could see it more if we did more digits and more numbers. Let's go up to 64. Okay, so here we have hexadecimal 0 corresponds to 000 in the bottom place. Hexadecimal 4 corresponds to the next 4 digits, 0100, which is indeed 4. Here, hexadecimal F means the bottom 4 digits, binary digits are all 1. Hexadecimal F there means they're all 1. Hexadecimal F here means they're all 1. So that's why hexadecimal is useful if you care about looking at the bits, the patterns of bits, because each hexadecimal digit maps exactly onto 4 bits. By the way, we could actually simplify this a little bit. For one thing, when you convert a number to treat a number as Boolean, any non-zero value is true and 0 is false. So we can simply do this. We can say number bitwise and of mask, and that will be treated as a Boolean value where any non-zero number is going to be 1, is going to be true, and 0 is going to be false. There's also an operator. Instead of using an if-else here, there's a more concise way in this case. Whether you prefer that is, I guess, a matter of preference, but we can say number, then we can use this question mark operator, which is a ternary operator because it has 3 arguments. To the left of it is the condition, and then we have 2 more arguments separated by a colon. We have the value of the expression if the condition is true, and the value of the expression if the condition is false. So this is a very concise way to output 1 if the bit is true, and 0 if false. So this will do the same thing. Okay, so far I've been talking about positive numbers, or at least non-negative numbers. What about negative numbers? Well, let's go ahead and modify the script we already created here, and let's just output some negative numbers. So far we've written 0 to 64. Let's try a few negative numbers. Before I do that, let me just kind of clean this up a little bit. I'm going to make a little function called writeNumber. And let's just put this code right here in this function. And that way, if we want to write a series of positive numbers, let's say that, we'll just say writeNumber. And then here we'll put number and number. And by the way, since each of these things is an expression, we can just put this whole, we can put this whole thing, instead of declaring a variable, we can just stick it right there. All right, that should give us the same output as before, except we're only going to write the numbers through 16 numbers. Okay, we're writing numbers from 0 up to 16. We're writing them in decimal, and then hexadecimal and binary form. It'd be nice if we could get these to line up nicely. Let's do that. So here we can in these format specifiers, in these little placeholder things, we can include after the index of the argument. So here, this 0, remember, is the index of the argument. In this case, it's the number. We can include comma and then the number of the width of that field that we want. So it's going to be padded with spaces. And we can do the same thing for the hexadecimal. We can say we want to make this have a width of 4. and it will be padded with spaces. And then when we write this out, now it lines up a little bit more nicely. Or if we wanted to, for the hexadecimal, maybe instead of having it padded with spaces, we can do it this way, say x4, and this means it's going to be a 4-digit hexadecimal number, so it's going to be padded with zeros. Okay. Only we're going to need 32 bits here to show negative numbers for reasons I'll explain in a minute. So let's make a couple more changes. So far we've been getting the binary digits. We've only been getting we've only been getting 16 digits from 15 down to 0. We have to go all the way from 31 down to 0 because we're going to be writing 32-bit binary numbers. And then when writing the hexadecimal, we're going to need, for 32 binary digits, each hexadecimal digit is 8, or each hexadecimal digit is 4 binary digits. So we need 8 hexadecimal digits to represent a 32-bit binary number. So let's write this again. Okay, so here's our new format. We show in decimal, in hexadecimal, and in binary, we're showing a 32-bit number, and we're counting up from 0 to 16. Now what if we count down? We'll do the same thing, but we're going to count down from, we'll go ahead and write 0 to 16, but let's also write -1 to -16. So here's some 0 to 16, and here is -1 to -16. So what is that? Well, you notice that -1 has all bits 1. All the bits are 1. And of course, in hexadecimal, that looks like FF, FF, FF. All the bits are 1, because FFF, or the F hexadecimal digit, corresponds to the bit pattern 1111. And then when we go down to negative numbers less than that, -2 and counting down and so on, we're simply counting down from that very large, what seems to be a very large number. Now, if this were an unsigned 32-bit integer, this number would be 2 to the 32 minus 1. I mean, this is, f is 2 to the 16 minus 1. F is 2 to the, f is 2 to the 4th minus 1. So it's, because it's 16 minus 1, it's 15. F. So this is essentially 4k, if you will, 2 to the 32 minus 1, if we're an unsigned number. When we're treating it as a signed number, then anytime this higher order bit is set, then the value of this number is its unsigned value minus 2 to the 32. So in effect, this is 2 to the 32 minus 2, or excuse me, this is 2 to the 32 minus, well, I guess one way to write this would be, this is f minus 100000000. Did I get the right number of zeros? 1, 2, 3, 4, 5, 6, 7, 8. Yes. So in other words, this number here is 2 to the 32 in hexadecimal. This is the largest possible 32-bit unsigned number in hexadecimal. It's 2 to the equivalent to 2 to the 32 minus 1. This is the bit pattern here that we have for -1. And its logical meaning is this number minus this number. And this number, 2 to the 32, is 1 greater than this number, so this comes out to -1. And of course, as we count downward, this number is 1 less than the number above it in an unsigned form. So it's going to be -2. And this number is 1 less still, so it's going to be -3, and so on. So that's how negative numbers are represented. This is what's called 2's complement. And the effect of that is that the largest possible positive number you can represent when you're using a signed integer, if it's a 32-bit integer, the largest possible positive number is going to be all the positive numbers have to have the higher order bit set. So it's going to be this bit pattern here. And in hexadecimal, that is 7FFFFF. That's because 7 corresponds to the bit pattern 0, 1, 1, 1. So because it's 1 plus 2 plus 4. 1 plus 2 plus 4 is 7. So 7 corresponds to the bit pattern 1, 1, 1. So 7 F, 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 F is the largest possible positive signed 32-bit integer. And it corresponds to a little bit more than 2 billion, or 2K. The largest possible negative signed integer, or largest possible, the negative, or the minimum negative signed integer, the one that's farthest from 0, the one with the largest magnitude, would have this bit pattern, because this is essentially equal to FF is equal to 8000000 minus 1000. Let's see. Yeah, I got the right number of things. 1, 2, 3, 4, 5, 6, 7. Okay, so this number is the smallest possible number you can get that has the high order bit set, right? So this is because the 8 corresponds to the bit pattern 1000. So this number here has the high order bit set, the bit 31. This being the bit indices go from 0 up to 31. So bit 31 is set to 1, and all the other bits are set to 0. So this is the smallest possible positive number that has, or unsigned positive number that has a high order bit set. And then when you subtract 2 to the 32 from that, you get the smallest possible signed, or the minimum signed 32-bit integer, which is, as you'll notice, is actually slightly greater, or has a slightly higher, one greater magnitude than the largest possible unsigned, or largest possible positive signed integer. Okay, so that's the long and short of this is that you can. It's sometimes important to understand that when you're dealing with numbers in a computer, when you're dealing with integers in a computer, there are limits to how big an integer you can represent. And those limits are based on the number of bits you have to store. And it's not too surprising if you think about, in mathematics, the integers are infinite. They go on forever. But if you're actually going to write down an integer on a piece of paper, you're going to be limited by how much space you have on the paper to write down your characters. You can, mathematically speaking, you can imagine an integer that has so many digits that you would need as many atoms as there are in the universe to write down that number, but you're never going to be able to write that down. And nor can you ever represent that number in a computer. But the numbers we work with in real life usually tend to be small enough that we can deal with it. To represent really large numbers in the real world, like in science, for example, if you do want to describe the number of atoms in the universe, you'll tend to use scientific notation. So you'll say, you'll not give the exact number, you'll give the number to a certain number of decimal places, and you'll say times 10 to the 100th power or something like that. So the equivalent of that in computing is to use floating point. So that will be the next topic to talk about. But I think this video has gotten long enough, so I might just stop right there and leave it at integers. So to summarize a little bit what we've talked about, we've described how computers use binary, represent numbers in binary, which is base 2, instead of decimal, which is base 10. And hexadecimal is just a notation that we can use to more conveniently describe binary numbers. Also, we can use certain operators, certain binary operators, to operate on bits. So we can use the shift left operator to shift bits to the left, the shift right, or SHR operator to shift bits to the right, which is just like adding zeros to the end of the number, or moving the numbers, shifting zeros off to the right side of the number, or shifting all the digits to the left and adding zeros on the right side. That's all that's doing. We can use the bitwise AND operator to perform a logical AND between the corresponding bits of two numbers without individually treating the individual bits. Instead of treating the whole number as a whole, we're actually performing the operation on each individual pair of bits. Likewise, there's a bitwise OR, VOR, and there are various other operators. But in this particular case, we're using it to mask off the bits we care about. And to do that, because bitwise AND is only going to be true if both the numbers are true, we can compute a mask that has only the bit we care about set to 1, and all the other bits are 0. And in that way, we can find out whether a particular bit is 1 or 0. And in that way, we can write a binary number. We can also use these number formats to write decimal and hexadecimal numbers. In this case, we're writing the string that we computed using our getBinary function. So I think that and just understanding that numbers have limits is maybe a good place to stop for today. Thank you for watching, and I hope to see you next time.